as natural languages like English or Japanese. It's good to use this language to get some idea of what exactly the notions are in terms of which we want to interpret these natural language expressions. Okay. So it's an artificial language, and like natural languages, it has a syntax and a semantics. And I think, well, I will go through this fairly quickly, but you tell me if I'm too fast, okay? Okay. So the syntax, what is it? Well, this language is a set of expressions, and we define it in the same way as we have defined sets before with these recursive definitions. So the language, as I call it on this handout, let's just say is called LA, where A is a set of letters of propositional variables. So we have A is a set of variables, things like P, Q, P1, P2, and so on. And they stand for things like it is sunny and John is at home and things like that. It can be true or false. So this is where we start, and then we say, first of all, that A is a subset of this language. Okay, this set of propositional variables, right? We may also call them atomic sentences, and I will probably say that sometimes. So they are the basic units. So A is a subset of this language. That's why we have the subscript here, LA. Okay, and then for every sentence in the language, for all, let's say if phi, some sentence, right, is in this language, then its negation is in the language. And if we have two sentences, phi psi, then various other expressions are in there. We have a choice here of how many of these sentential connectives we want. Let's just say on the handout, I think I have 3 binary ones. Yes. So the conjunction, phi and psi, the disjunction, and the material conditional, they are also in LA, and nothing else, right? So those are the only things for now. This is not modal yet, right? So we have sentences like the ones depicted here on this handout. We can build them up using these rules and sort of prove that, for example, the sentence not R or Q, P, not R or P, and R, that this is a sentence of the language because we can take it apart each time following one of these rules by just pattern matching, right, and showing where it comes from, that is built up from these atomic sentences. This is here, it's a conjunction, right, it matches this, where our phi is this and our psi is this. So I give you this parse tree on the page, and we have not R or P, here we have R, and they are connected via this conjunction sign, and so on. We can do this to the bottom of this tree. You have it on your handout, so I don't have to write the whole thing on the board, right? Or maybe I should. Well, not necessarily. It's okay. So these rules determine what is in the language and what isn't. And that's all there is to the syntax. And I will sometimes drop these parentheses, like here I already did it, when there is no danger of ambiguity. Okay? All right, so the semantics of this now, well, I sort of have to deal better with space here. I said these propositional variables are things that can be either true or false, and that's all there is to them. Okay? So the semantics for this language is a very simple thing. We just say that sentences are interpreted by assigning truth values to them, and the only interesting thing that we get out of this is a way of determining, given the truth values of two sentences, what the truth values of their various compounds will be, right? On page 15, second paragraph, it says, formally, each connective, blah, blah, blah. This should be each truth assignment. I don't know. There are some typos in here. I'm sorry. Okay. But it is a function v for valuation or truth assignment, which just, we start, say, by assigning truth values to the atomic sentences. That is, we go from this set A and assign values 0 or 1, false or true, to each of the atomic sentences, right? And then we can follow the structure of more complex sentences and determine how the truth values of complex things depend on the truth values of their constituents and the way they're put together. And you hear these phrase very often as, sort of definition of what compositionality is supposed to be. We see in figure 2, top of page 15, for each of these connectives here, conjunction, disjunction, this material conditional, negation, how the value of the complex sentence depends on the value of the simple sentence. Are you all familiar with these things? Truth tables, how to truth functions, everyone? Well, you should say so. Okay, so you don't have to go through it. Well, perhaps just this simple example. So we start here perhaps with R, right? And now suppose we have a function v1, say, right? So v1 of R is 0. You see where I am here on this page in the table 2, figure 3. So figure 3, v1 of R assigns 0, and then by the clause for negation, the line that corresponds to negation, or the row, so the row for negation in the upper table, we see if a sentence phi has value 0, then the negation of phi has value 1, right? Just look across. Do you see how this works? So we have this negation sign here which gives us not R, and v1 of R is 0, and whenever the value of a sentence is 0, then the value of its negation is 1. So we know that v1 of this is 1 by this truth table in figure 2. Is that clear? Right, how these are supposed to be used. Right. And if we do this for the whole parse tree there, the syntactic tree on the bottom of page 14, we get a truth value that sort of pops out at the top. So we have not R here. This again combines with P by disjunction, right? And v1 assigns 0 to P as well, right? As well as to R. And so from these two things, we have a 1 here, a 0 here. We can look this up for phi and psi. If phi has value 1, psi has value 0, value of the disjunction is 1, that we see in the upper table, right? The line for 1 and 0. So we have not R or P, and this is true. And finally, we get R again. And we already know that this is 0 here, right? And so we have 1, 0 combined via this conjunction. So we know that B1 of the whole sentence, which I won't write, it's on your handout, right, is 0. Okay, so for two sentences now, we have 4 possible ways of assigning truth values, right? Four that are listed here, V1, V2, V3, V4. This is simply because they are functions from some set to a set with 2 members, right? So we get 2 to the cardinality of A as the number of possible truth functions. If we had 3 sentences, we would get 8 lines in the truth table. This is shown on figure 4, page 16. So if we have a third sentence, we get 8 lines in our truth table. And now, it's useful to think about this a little bit. So the number of possible states of affairs that we can distinguish depends on the number of sentences that we have. That is pretty clear. That is the expressive power of our language. But perhaps we don't want that. Maybe there's a sense in which states of affairs are something that exists independently of our language that we use to describe them, right? Somehow it's useful to say that the fact that we use a language with 2 sentences is just an accident. There still are 8 or more, however many different possible states of affairs, right? In that case, our 4 valuation functions that we started out with, they really capture classes of states of affairs, right? So V1 is the class of all states of affairs in which P and R are false. V2 is again a class, not just one states of affairs in which P is true, R is false, and so on. And in principle, there are enough states of affairs for however many atomic sentences we want. There should be enough possible, so in the abstract sense, possible states of affairs. So I'm doing this long-winded derivation here just to motivate this notion of a possible world as precisely this kind of theoretical construct. Okay, it is what we would get if we were to add more and more atomic sentences until we hit some limit. There is no limit. There can be infinitely many. Okay, but the things that we get an ever finer and finer view of if we do this, right? Things we can distinguish more and more finely. Those are the possible worlds, the endpoints of this process of refining, right? Going from 4 to 8, and then to 16, and then to, well, more and more. So those are possible worlds, and those are the things we work with in modal logic. And it's also useful to realize that even though there are many philosophical debates over this notion of a possible world, they don't have to concern us at all, not in the least. Philosophers worry about these things. Do they really exist? What does it mean? How do we know what they are? Is there more than one possible world? We know of only one, this one, right? This exists, but is there, and in what sense? That's completely irrelevant for these purposes. for our purpose, for semantics, they are just a way of saying something about the relationship between various linguistic expressions, nothing more. Okay. Okay, so this takes us now to possible worlds and the models that we get in modal logic. In the so I'm here on the page 17 on the top. I have a few of these things that I just said and some more remarks on how it all started, who invented these things, and so on. You don't need to go through that here. It will be on your handout. The modals now are slightly different from what we saw in the non-modal logical case. So we take the second step now to propositional, still propositional. That is, we don't have variables over individuals and so on, right? We only have these propositional variables or sentences. Propositional modal logic. And I will use the same name for the language, LA. Okay. The syntax is slightly different and the semantics is also slightly different. This time I will start from over here and start by talking about this notion of a possible world some more. The truth assignments that we had, these four V1, V2, V3, and V4, as I said, they distinguish the possible worlds, right? If we are given a set of possible worlds, then each of these worlds determines the truth values of all atomic sentences. Okay, that's what they do. That's their only role. If you are given a world, W, then every sentence is either true or false in that world. Okay. So from basically, we only change our perspective a little bit from this here. We had before an interpretation just being a distribution of truth values over these atomic sentences. Okay. Now, every possible world is something like this, and we have many of them in one model. Okay, so what we can do various implement this in various ways. The most common way is to say that V is not just a function from sentences to truth values, but a function from worlds to that kind of thing, right? So that means where before we said things like V of P is something 1 or 0, right? Now we have to say which V we mean, the one of world 1 or world 2, right? So for some given world W, we write VW of P as such and such. That's the only change. That's all. Okay, so the truth of we still, on this side here, on the syntactic side, we still don't have notions of necessity and possibility and so on. But we already have this kind of model. And the truth of complex sentences, again, depends on the truth values of their constituents in exactly the same way as before. So in particular, for example, for negation, VW of the negation of P, right, is 1 or 0. It is 1 if V of P at W is 0. It's 0 if VW of P is 1. This is the same thing as saying that when you have a sentence phi and 0 and 1, then the negation of phi is this. That's what we had in figure 3 before, this sort of format with more connectives, right? It's the same as, just writing it this way. These recursive clauses in 16 on page 18. They are actually used more commonly, I think, than these truth tables. But if you look across between 16 and figure 3, the information is the same. They describe the same functions. Okay. So the conjunction is true if both constituents are true. The disjunction is true if at least one is true, and so on. And since you have all seen this, I think we can move on. Is it okay? Yeah, so this is an alternative format for saying the same thing. Okay. Now the next step here on 17, I say that we can now use these functions. Now suppose, so look at here. For any sentence phi, we can think of v of phi. Now this may be some complex, large structure. We can think of this as a function from worlds to truth values. There is a way of defining it, right? Swapping this. So if we apply it to W1, it may be 1. If we apply it to W2, it may be 0, and so on. It's a function from worlds to truth values. That means it's what's called a characteristic function of a set of worlds. Right? Because it's true in some and false in the others. It identifies, picks out a set of worlds, namely precisely those in which the sentence is true. And we can call the denotation of the sentence that set of worlds in which it is true. That's what it says in 17, right? These double brackets for some sentence. There is a superscript here, M, for the model. I haven't put this M anywhere yet, but let me leave it there. Is a set of worlds such that sentence is true in those worlds. That's fairly straightforward. Now what is this M? Well, M, a model, currently it's just a pair, right? We have a non-empty set of worlds, and we have this function of this type from worlds to truth assignments, right? It's a model. And in this model, sentences identify sets of worlds. Not only atomic sentences, but all of the compound sentences, because they all have truth values everywhere, right? Okay. Now, in terms of these possible worlds, we have here a set of possible worlds. Now we have a set theoretical way of saying things about the sentence that denotes the set, right? So we can say, for instance, what it means for the sentence to be a tautology, right? Something that cannot possibly be false. It's pretty clear now. It is simply a sentence whose denotation is the set of all worlds. Now here in 18, I write W is a subset of the denotation of the sentence. That's sort of a cute way of saying the same thing. I mean, the sentence cannot denote more than all of W, right? So if it is true in all possible worlds, then it is a tautology. And of course, simple examples are simply P or not P. Given the standard assumptions of propositional logic, this cannot possibly be false. So this is something whose denotation is W, that's a tautology. Likewise, contradictions are just the opposite. Here I say, or in B, the denotation of phi is a subset of the empty set, which can only be the case if it is the empty set, right? So in the case of P and not P, that's a contradiction that denotes the empty set of possible worlds. Okay. And then a contingent sentence. That is something that is actually interesting, right? That's something that carries information, so to speak, because it's true at some worlds and false at others. And those are the interesting ones. Is that pretty clear? Yeah. Now, if we are given these sets of worlds that sentences refer to or denote, we can line up logical connectives like conjunction, disjunction, and so on, and set theoretic operations in the way I do in 19 on the handout. Right? So the denotation of two sentences that are conjoined, like these, P and not P, this is simply the intersection of the denotation of P and the denotation of not P. And this has to be the empty set because there is no world at which they are both true, right? Similarly for the disjunction, now it gets a bit tricky here. This goes here, so. We have the union of the two sets as a denotation of the disjunction. And for the negation, we have the complement. That's all in these clauses in 19 on the handout. Right. If we have a set of sentences, this will also be useful tomorrow in the readings. If we have a set of sentences, I use this uppercase, this large, big phi for that. Then we can also give it a denotation in the model, given here in 20. And this is written like this here. It's a big intersection of a large set, right? So big set of propositions phi, such that phi is in this. So for example, if we have a set of sentences P, Q, and R, right, then we can say that its denotation is, well, it would then be this, right, this large P, Q, R, which is a shorthand way of writing P and Q and R intersection of each of these propositions of each other. So it's, in other words, the set of worlds in which all of these things are true. This is just generalizing a little bit from what we saw with the conjunction. You don't have a syntactic symbol for more than two. Conjunction only combines two things at a time, not three. But a set of things can nevertheless have a denotation that is of the same kind as if these three things were conjoined, right? And it's simply the intersection of all the propositions that are in there. Let's just set propositions, right? First time. A set of worlds is a proposition. All right, and so the notions of contradiction and tautology and so on, they are now helpful in making statements about sets of sentences like this, phi, okay? Because this disjunction, just like, this big intersection here, just like the conjunction of P and not P, may be empty. Namely, if these three sentences cannot all be true at the same world. Well, if it is empty, then phi is inconsistent. 21 gives this denotation, this definition of consistency. It's consistent if there is some world in which all the sentences in phi are true. Right? These are really the central notions of modal logic: consistency, consequence, so on. And it's, we can also say a sentence is consistent with a set of sentences. So we can say that phi is consistent with this set if and only if this is consistent. Now, what is this? Well, for instance, if our phi is, again, say P, Q, and R, it's P, Q, and R, right? This be phi. And then consider a sentence S, say, and we are asking, is S consistent with this set of sentences? Well, we put these things together according to this definition. That's what it says, right? We take the union of phi and the set containing that sentence, which is what I did here, PQR, put together with S. So we get the set of 4 propositions, 4 sentences, right? P, Q, R, and S. And if they have a world in which they are all true, then S is consistent with this set. Okay. So we have set theoretic ways of stating all these properties of sentences, and also relations between sentences, like S is consistent with this. All right. Now, consequence, S is a consequence of phi. Well, so phi is a consequence of this uppercase phi. Well, under what circumstances? Well, if the worlds in which all the sentences are true also make phi true. Let me write this down first. If so, this is a subset of this. That means, now talking in terms of these diagrams again, so we have P, Q, and R. We see there is a non-empty intersection. If this is the case, then the 3 are a consistent set of sentences. Okay? Right? If there's, so all of these things are sets of worlds. Okay? Are you following me? Right. Well, let me write this in a more pedantic way. Perhaps this is more conspicuous. So each of these sentences denotes a set of worlds in W, right? And the 3 together are consistent if there are some worlds here in the intersection. If the intersection is not empty, according to this definition in 21. Right? Now adding S, a sentence S to this set, just, puts another circle in here. Suppose S is this. Denotes this set of worlds. If we put the 4 together, and there is still a world in here, now where all the 4 sentences are true, then S is consistent with these 3 others, right? So it all depends on whether there is some world in which they are all true. Now S in this case here, the way I drew this, is not a consequence of the 3 sentences, because consequence is only that if this set here is a subset of S. If S follows from the set of sentences, that is, whenever all the 3 P, Q, and R are true, then S must also be true. That's not the case in this picture there are some worlds in which the 3 are true and S is not, so it doesn't follow from the 3. Right? But if S were to go all the way here, like this, then it would be a consequence. So consequence corresponds to the subset relation. And consistency has to do with non-empty intersection. Those are the two things that we need to keep in mind. Right. So, yes. Hi.
コンシステンシーとコンシクエンスの定義で、これは一つの与えられたモデルに相対的に定義される無矛盾性とか、コンシクエンスの概念と考えていいんですよね。
はい、今はそうですけど、はいはい、まあ、何を言おうとしているか分かりますけど、はい、結局は V に関わらないですね。モデルに関わらない。結局は、はい、もうちょっと後ですね、話が。いいですか？はい、
だから、sentence phi is consistent with a set phi of sentences with respect to empty.
そうですね、実は。それはありがたいですね。はい、so, perhaps I should like to say this in English, but you're right. So, you actually have to distinguish two things here. It may be that S is a consequence of these 3 sentences simply because of the way we set up the model, right? On the other hand, it may be that S is necessarily a consequence, however we set up the model, right? It is necessarily a consequence if we are talking about things like these tautologies, like P or not P and so on, right? It cannot possibly be false. When it's about contingent relations, then we have to be a little bit careful. But we will models and frames. We will distinguish between validity in a model and validity on a frame, and then it will be clear. Now I'm talking about model. It's all relative to a particular model. Yeah. Thanks, that's important. But so the next step is still not talking about modal operators here. That comes later. To ask now, the next step is to ask what is a modal base in this picture here, right? Because, so to back off a little bit, I said earlier in the introduction that modals always assert that a sentence is either consistent or a consequence or somehow follows or stands in some relation to a body of information, right? Like a state of beliefs or laws or obligations, things like that. Okay. Now, such a body of information can be given as a set of sentences, all the things that you believe, for instance, right? In principle, not in practice, but in principle, we could write them all down as sentences. And then all your beliefs together are, well, a set of sentences like this, phi. They can be consistent or not, so on. And they also then correspond to a sets of worlds. Right? If we have 3 sentences, P, Q, R, and each of them denotes a set of worlds. Okay? Then the set of the 3 sentences is something like this, like these 3 white circles here, right? And the worlds in which all of your beliefs are true are the intersection. So the things you believe, right? P is true, you believe R, and also Q. Your state of beliefs can be represented as the intersection of all these sets of worlds, right? And that is the body of information that I was talking about earlier. And that is the modal base. Modal bases are this kind of thing. Right? And if you have a modalized sentence like it may be that P or must be that P, so on. They say that P, well, here it would be a bit like our S actually, right? Maybe that S must be that S and so on. These sentences say that S stands in some relation to this modal base. Okay, so that's the idea. Modal bases are, well, we can start by having a set of these sets of worlds and then take the intersection. We can also just say for now, tomorrow we'll actually do this. For now we can say a modal base is simply a set of worlds, period. Okay, it's a set of worlds, that's all. Like this intersection in here. So yeah, and then we have to represent modal bases somehow in the model. We have to say what is actually the modal base. Now that is, for example, if it's a set of beliefs, which beliefs you have is itself a contingent fact. That is, at each possible world in the model, you may have different beliefs. That has to be possible, right? Because I don't know which beliefs you have. That means my beliefs are consistent with different sets of beliefs of yours. So there must be different possible worlds. One in which you believe that today is Friday, perhaps, and the other one in which you believe that today is Thursday. And then in each of these worlds you know what day it is. But I believe that you, sorry, I don't know which one it is, right? I don't know whether you think it's Thursday or Friday. So there are two possible worlds, one Thursday world, one Friday. So I'm just, to make a long story short, what I'm trying to say is that the modal base has to depend on the world in which we evaluate the modal sentence. So something like may P may be the case, or it may be the case that P, right? We want to do the same thing to this kind of sentence that we did earlier to the other sentences. That is, assign truth values relative to possible worlds. Here. Okay. And since the sentence asserts actually that P is consistent with the modal base, the modal base too has to depend on the world of evaluation, right? Because obviously whether it's consistent or not with that modal base, well, that varies from world to world. Am I clear? Does this make sense? So we might say, so the value of this, say we have W1 here in the model. The value of the sentence is perhaps determined relative to this set of worlds. This is the modal base at W. So if we have an epistemic reading for the modal, this is a set of worlds that is compatible with the beliefs of the person in question. Okay? At W1. At W1, you have certain beliefs. These are, well, they happen not to include W1. That's okay, because your beliefs may be false. Maybe you think today is Friday. So if it's actually Thursday, then W1 is not included. And now we ask, is P consistent with this set of words? Right? If it is, then the sentence P may be true is true at W. The sentence, it may be that P is true at W, whenever P has some overlap with the modal base. So suppose this is P, right? So at W1 the sentence is true in this picture. Now if we have W2, then we may be talking about a different modal base because your beliefs are something else. Perhaps your beliefs are this set of worlds. The modal base at, this is this should be W1, this should be W2, base at W2. There is no overlap here between P and that set of worlds. So we would say then V at W2 of this sentence may P is 0. Okay. Now there are two things here. First of all, notice that P is false at both of these worlds, right? And that's as it should be, right? Because these are not assertions about the actual truth value of P, but about the compatibility of P, or the consistency of P with the modal base, right? And then secondly, the modal base changes from world to world. Changes from world to world, and that's how the truth value of the modalized sentence can also change. I'm getting, I don't know, are you with me? Or do you understand? Is it okay? You're staring at me then. Tell me what. Yeah. So this, now we see here that the modal base, what should it be formally in the model? What kind of object should it be? Well, it should be something which at W1 gives you a set of worlds, and W2 gives you a set of worlds, and so on. So a function from worlds to sets of worlds. That's the simplest way of encoding this modal base. That's what it is. And then we say, when we have this, say, with an epistemic reading, then we choose the epistemic function from worlds to possible worlds. And then we have a deontic one, because what you believe may be different from what is required, or what you want, for desires, booletic, how this is called. You may desire different things from what's allowed, for instance. So different modal bases may end up in quite different regions of this overall space of possible worlds. But each of them depends on the world of evaluation. Right, so now where do I say this in the handout? This must be somewhere. Formal representation, top of 21. So here I call it a function R, which, as you see, is a function from worlds to functions from worlds to truth values. That is a cumbersome way of saying it's a function from worlds to sets of worlds. Okay? So R, we can say things like, or we can call this now, where I wrote modal base for W1, this is simply RW1. Let's just write that, okay? And we have RW2 down here. Both of these are sets of sentences. Okay, and R is the thing which, when given a world, gives you a set of words. Is that clear? Sets of. Did I just say that there are sets of sentences or sets of words? Never mind. Sorry. Okay, so that's the modal base. That's how we encode it in the model. So eventually the model will have to be something that has a set of worlds, these distributions of truth values, and then this R. That will be part of the model. It will be three things. And the modal force, that is now pretty clear what that should be, right? We talked about modal force being necessity or possibility, right? In other words, universal quantification or existential quantification. Or in still other words, consequence or consistency. A possibility model like this just says P is consistent with the modal base. A necessity model says P is a consequence of the modal base. So there's these two different things that we have to distinguish, and that is the other parameter in the interpretation of modals. Modal base, modal force. Tomorrow there will be a third one, the ordering source. But that's for tomorrow. Okay, well, we have to put this together into the model and actually make sense of it, really. So we have here a sentence, actually, 23a, right? John is at the party, and then we have these two modalized statements about 23a. John may be at the party. John must be at the party. And here in this paragraph underneath, giving the truth conditions for sentences like this, I introduce these two operators that you see in the philosophical or in the logical literature on modal logic. Here I wrote may, right? And we may also may also have something like, P1 of must P is 0, I guess, right? Because P is not a consequence of this modal base. And so on. Now in modal logic there are symbols for this, right? And they are the box and the diamond that you see. So if a sentence phi is in the language, then this sentence, box phi, right? And this one, diamond phi, right? They are both also in the language. And nothing else. And just to remind you, the idea is that they are necessity and possibility respectively, or say consequence and consistency, right? Must and may. Those are the two things that logicians use in their theorizing. So we have these things together now at 24 and 25. You see, this is basically what I've said over here already, right? These clauses, just with these symbols substituted for what I had here. So the value of, how should I write this down? Over here, we are in semantics, right, after all. So the value at a world W of this sentence, possibly P, or let's say phi, where this R is some particular modal base, right? Some particular reading of the modal, deontic, epistemic, whatever. And now here well, actually, yeah, let me write this. This is one if V W prime of phi equals 1 for some, there's a typo again in both of these lines. There's, okay, I'm getting there. For some W prime in RW. There you have a Greek little row. That's supposed to be the same as the R. Sorry about that. And the necessity modal is defined as, 1 if this is the case, and then I have 0 otherwise, right? And the necessity modal R phi is 1 if V of W prime phi is 1 for all W prime in RW, 0 otherwise. this is the textbook definition, right, of these operators. In fact, usually only one of them is defined in these terms, and the other is defined in terms of the first one. So, because it's always the case under this definition that this is true if and only if not, possibly not phi is the case. So I must go to the bathroom is the same as I cannot but go to the bathroom. I cannot not go to the bathroom, right? Something like that. So, and it works in the other way as well. Now you may actually see here, if you're careful, you see a difference, in fact, between these definitions and the definition in terms of consistency. Because there I would have said something slightly different, and I won't write it down here because we will stick with this, at least for today. I would have said something like, the possibility modal is true if and only if the intersection is not empty, right, between RW and this denotation, right, brackets, sentence. It's the same. Down here I would have said, this is true if and only if RW is a subset of this denotation of the sentence. Okay. Now there is a problem here. If RW is false, empty, if RW is empty, if the modal base is empty. Oh no, that's actually not, sorry. What am I trying to say? No, oh, in both cases, sorry, in both cases this comes out true. Right, both cases. Yeah. Comes out true. If the modal base is empty, then anything follows from it. That's because the empty set is a subset of everything. Or alternatively, it's always the case that all worlds that are in the empty set are also in some other set. That is always true. We'll stick with this, but remember that you could say the same thing in terms of set relations. Right, so, an hour is gone. This is good. Let's have a little break, okay? 15 minutes. And then I will talk about accessibility relations. Okay, yeah, good. So see you in 15 minutes. This picture. So let me go over this once more, just quickly. Basically, how is this definition related to this picture? Is that the question, right? Yeah. So we can get rid of this definition of the syntax of the language. But so the idea is, again, we want to know at W1, is this sentence, as earlier I wrote may as a word, now we can just say possibly with regard to R, right? P, right? What is that? Is it true or false? That's the question. And the truth value is the truth.